We'll start. Our last speaker of the morning is Andrej Bogdanov of University of Ottawa. Take it away, Andrej.
Thank you very much, Ryan, and thanks to the organizers for inviting me to this wonderful workshop. I was lucky to be selected for something called administrative processing, so I couldn't make it, but I hope to catch up with some of you perhaps later in the semester if you're still around. I'm going to be talking about joint work with Alon Rosen, and it's not very much of a meta talk, but it does relate to average case complexity and a bit of cryptography perhaps. So I want to start at the very beginning, right? We are complexity theorists, and when we teach complexity in 7th grade, this is what we teach, right? There is P, there is NP, and then there is SAT, right? And okay, so then we talk about all these other wonderful things like clique and subset sum and vertex cover, and they all happen to be the same as SAT, right? So it's a simple picture, it's nice, and then the students usually conclude that NP means not P, right? That's what the picture. It's consistent with the picture, and actually we have to work pretty hard to find things that are, in this space between NP and P, which are not the same as SAT, right? And some of the people in this audience did some of this wonderful work, and now we have such examples that we can ponder about, but we really have to work hard to do it, to find them. And I want to contrast this picture with the distributional picture, so average case world, which looks nothing like this, right? So there we have like the analog of SAT is this bounded halting problem, and Levin's theory from the 80s tells us that, we have something on top that we should expect, as a basis for showing that things are hard, but we haven't been very successful at finding reductions. And, essentially we understand now that these problems are really about, we do have some problems that are complete, but they're all essentially about Turing machines, right? They are the meta stuff, they are the meta problems. But then there's all these other things that we care about, right? And they are kind of isolated islands in this landscape. Like we cannot really relate them to one another. Even if we talk about a single problem like SAT, like depending on how we pick the parameters, it's not clear how to relate one version of the problem to another version. So a lot of it is a mess. It's something that we don't like to talk much about. So we don't. Last year, or actually in 2021, I was at the Simons Institute at this wonderful program on statistical inference. And one of the highlights of that program was this network of reductions that is largely from work of Brennan and Bressler from 2020, where they wanted to explain why some problems that come from machine learning and statistics exhibit computational statistical gaps. And what this means is that
the upside down.
Well, the way that we draw reductions in complexity theory, yes, right? We start with the easier ones and we go to the harder ones, right? They draw it the wrong way, but we cannot do anything about that. So, so yes, it is supposed to be upside down. And so the motivation for their work is they try to explain why some problems where you're trying to learn from samples, there are gaps where if you're not given enough samples, then you can in principle learn statistically, but there are no efficient algorithms. And they developed this nice network of reductions that, well, it's not perfect, but it shows that under some conjecture, they can actually explain where a lot of these gaps come from. And, so it's not exactly clear that there are no reductions in the distributional world. They exist, but it's much less clear when we can expect to have them and when we cannot expect to have them. And as complexity theorists, that is our job, right? To explain what happens. And so that's what complexity theory is, right? If we want to show that problem A is no harder than problem B, then we have reductions, right? That's what reductions are for. But we also want to sometimes explain why is it that we don't have reductions, right? Why is it that two problems are of incomparable hardness, or one is not easier than the other one? And how do we show that? Like, what are the tools that we use for that?
Often give a model where B is easy and A is hard.
Yeah, so we need some kind of separation or oracles, right? And I mean, complexity classes are sort of a good convincing argument for doing that, right? So if you have some class of problems A that does not capture all of B, then showing that the problem is in A means that there is no reduction. So, I mean, in the worst case world, there are such examples, right? So we also, maybe not in 7th grade, but in 9th grade, in 10th grade, we say, well, you know, we have this factoring problem that people really are interested in, and it's not NP-hard. And right, and why is it not NP-hard? It's because there is this other class co-NP, right? So it sits in the intersection, so we don't expect it to be NP-hard. And then, you know, there are other examples, discrete log, shortest vectors, and so on. And it's the same kind of argument. So we can actually use complexity theory to argue, right, why one problem might be not harder than the other. So that's what I want to focus on today. And then, so if we want to kind of have a finer understanding of this hardness, then we can look at other subclasses like statistical zero knowledge, which is like essentially an NP intersect co-NP, and we can ask what happens there. But in the average case world, we don't use this kind of reasoning so much, right? Maybe in cryptography, we do have some oracle separations, but when we talk about these kind of concrete problems, and again, like some of these are really interesting, like a lot of you in the audience did this really amazing works on MCSP, MKTP. They do have worst case to average case reduction, so we really want to know what happens in this world, but we don't really have so many separations. One, I think, very interesting separation that does exist is from this work of Feige, Kim, and Ofek in 2006, where they showed that random SAT for certain parameters, there is some setting of parameters if you pick a random SAT formula in the unsatisfiable regime, where you have more clauses than variables, where we don't know how to solve it, so we don't know how to algorithmically certify that it's unsatisfiable, but there do exist some non-constructive witnesses that we can verify. So they showed that SAT, I don't know, with close to variable density n to the 1.4 or something, is actually has an average case algorithm, but it's a non-deterministic algorithm, right? You need to give it a witness, and it only works well on average, right? So I think it would be nice to have more examples of such problems and more natural examples. You know, not necessarily to advance meta complexity, but just sort of to play with. I think one of the arguments that you give that MKTP, you know, is not in right. You know, that reduces from these things like leak or SAT, which we saw in the workshop, but then we don't expect to have reductions in the other direction. And the problem I want to talk about today is called the nearest Boolean vector problem. So it's this simple, very natural problem, which was introduced in work by Mohanty, Raghavendra, and Shu in 2020. So the question here is, we have the Boolean cube, m-dimensional Boolean cube. And now I take some subspace, n-dimensional subspace, linear subspace. And I want to distinguish between two cases. In the yes instances are subspaces which are close to the cube, and the no instances are subspaces which are far from the cube. And here, when I say far from the cube, I put this 1/2. Like, so square root of m is like the norm of the vertices of the cube. Why did I put this square root of 1/2, this 1/2 here? Because what they're really interested in the no instances is what happens when this A is random. Right. And there is a natural distribution on subspaces, right? I can pick a random n-dimensional subspace. And they actually argue that in some natural setting of parameters, which I will explain why they're interested in a minute, that most subspaces are like that. And actually, it's not 1/2, it's some constant, like, I don't remember, 2 over pi or pi over 2 that they calculate, where they say that most subspaces where the ratio n over m is a sufficiently small constant are actually quite far from the Boolean cube. Why are they interested in this problem and the complexity of this problem? The reason they were interested in is because of another problem that again comes from statistics, I guess, and optimization. And this is the question of optimizing what they call the Sherrington-Kirkpatrick Hamiltonian. So this is purely motivation. It's not going to play a role later in my talk, but it's a very nice question and it's a very interesting connection. So I want to tell you about it. So what is the Sherrington-Kirkpatrick Hamiltonian? So you're given some matrix M that is essentially a random matrix with real numbers, random symmetric matrix with real numbers. Is chosen from something called the Gaussian Orthogonal Ensemble, which essentially says that I choose the entries to be random normals, independent normal random variables, condition on it being symmetric. And what this problem asks is to optimize the form X transpose MX, where X itself is a vector in the Boolean cube. And I think this was proposed back in the 70s as some kind of model of spin glass or something. I don't know exactly the history, but it's an interesting combinatorial problem in its own right. And it turns out that this maximum for most matrices can be bounded. And one way to bound it is to just replace the Boolean cube with the ball, right? So instead of optimizing over the Boolean cube, I can optimize over all vectors of a norm square root of M. And then what this quantity turns out to be is just the largest eigenvalue of the matrix M. And this is well studied for random matrices, and it turns out to have value which concentrates around 2m to the 3/2 in the scaling that I used. And what they're actually interested in is not this m to the 3/2. There is no mystery in that, but this constant 2. Okay. And the reason it's interesting is because it turns out that this 2 is an overestimate. It's not the right answer for Sherrington-Kirkpatrick. And this is a famous constant called Parisi's constant. What Parisi conjectured and then Talleyrand later proved is that the actual value is something that is strictly smaller than 2, 1.526. Actually, I mean, this is only a special case of some optimization problem that they looked at. This corresponds to the zero temperature regime. And what Parisi gave is a whole formula for this, which is very mysterious. And this is a whole other story. But this is the motivation. And what happened much more recently, and again, this is something I learned at the Simons, is that Montanari asked the algorithmic question, right? So this is a fact which is true about most matrices, but if I give you a specific matrix, what is the complexity of finding a solution to this problem? And in our language, what he shows is that there is an average case heuristic algorithm. So for most matrices, it finds a solution which has value close to this Parisi constant, 1.526. So that's nice, right? But as, again, complexity theorists, we're not super happy with heuristic. We want something which has better guarantees, right? And what's better to have than a heuristic is an actual, an errorless heuristic, something that always gives you the right answer, but maybe, you know, doesn't work on all instances. Sometimes it can say, I don't know. And so, okay, my slide is a bit messed up here, but what Mohanty, Raghavendra, and Shu were motivated by was exactly this question. So they asked, is there an errorless heuristic for this algorithm? And the way that they try to tackle this problem is by giving a reduction from Sherrington-Kirkpatrick to the nearest Boolean vector problem. And it's not a difficult reduction, but it's outside the scope, so I'm not going to tell you what it is. But what the result essentially shows is that if I can show that nearest Boolean vector is has errorless heuristics, or in other words, it has refutations, right? That in the case when most of the instances are hard, I can certify that they're hard, that they don't have a solution for a certain setting of parameters, and the setting of parameters they need is that where the dimension, the relative dimension is a constant, you can think of it as the rate, and the distance is also a constant, right? So it's some fraction of square root of m. And if you can find refutations for this nearest Boolean vector problem, then you automatically get certificates that Sherrington-Kirkpatrick is, well, at least it beats the spectral certificate of 2. It's a little bit less than 2, maybe like 1.99. Still far from Parisi's constant, but at least it's the first step that you would have to do. So that was what they first wrote in the paper, but then they gave negative evidence. So they said, well, how do we and how are we going to find this this heuristic, this errorless heuristic, this refutation? And well, they're going to use the sum of squares algorithm, which is what a common algorithm for this kind of settings. And there, what they proved is that sum of squares doesn't work. Actually, it thinks that if I give it a random subspace, not only is it not far from the Boolean cube, but it actually has a vector which is in the Boolean cube. And there were some technical improvements later on the parameter settings to which this applies. But the punchline is that kind of even in the very extreme case of this problem, sums of squares cannot distinguish random subspaces from subspaces that contain a Boolean vector inside them. So what is our result? So what we show is that even though we don't have an algorithm, that at least there is some regime of parameters. So I will explain what it is, in which refutations do exist. And in fact, this average case problem sits in average case statistical zero knowledge. So it's somewhere inside NP intersect co-NP. Right. So the setting of parameters here is you should think about n divided by m, the rate as being slightly less than a constant. So this is close enough to what they get. But what's weaker in the result that we get is that this parameter gamma, which tells you how the proximity to the hypercube in the less instances is not a constant, but it's something that depends inverse polynomially on all these parameters in the problem. And epsilon here is the fraction of instances on which this algorithm is going to fail. So it cannot certify that all subspaces are not in the Boolean cube. In fact, that's an NP hard problem, but it can certify that all but essentially 1/2 to the n of the subspaces are not in the cube. So what I want to do for the rest of the talk, I want to tell you a bit about how we came, how we stumbled upon this result, some connections to some work that we in cryptography, which is more than 20 years old, and and then conclude with some open questions at the end. So a corollary of this work is because we know statistical zero knowledge is in AM intersect co-AM, that we can actually certify that if I give you a random subspace, that it's far from the Boolean cube. So we get certificates, interactive certificates for this. And again, so this is kind of like the same situation as random set in the sense that these interactive certificates exist, but we don't know how to compute them. And right now, we don't see any reason to believe why they should be efficiently computable. So to get you a sense about what these certificates look like, so I'm not going to actually talk about SDK. I'm just going to try to tell you how would I prove to you that the matrix is far from the Boolean cube. Here are two matrices. So one of these is actually close to the Boolean cube, and one of them is far from the Boolean cube. I mean the column space of these two matrices. So if I think of the space generated by the two column vectors, one of them is random, and one of them actually has a point which is close to the Boolean cube. Does anyone have a guess of which is which? Okay.
A.
A is the one which is close. Okay.
Yes.
Well, I mean, okay, this is a bunch of numbers, so we cannot see it. So let's plot them, right? So this is the plot, right? These are the numbers. And actually, I have to tell you that I cheated here. I didn't actually put something that's in the Boolean cube because that would be a bit too obvious in 2 dimensions. But I still chose, I planted an integer vector inside, something that has integral coordinates, like 0 ± 1 ± 2, right? So again, these are two sets of points, right? And one of them has some, like, belongs to, like, has some integer vector in the column space, and the other one doesn't. Do you have a guess now about which one might have the integer vector inside? Like, do you see any lines here? Not clear, right? So here is the idea. The idea is what happens if we take random plus minus one combination. So we hit both these matrices A and B on the left with a random plus minus one vector. And this is the picture that we get, right? So this is just some kind of distribution over vectors, which is I hit the matrix A with discrete vectors on the left, and I hit the matrix B with discrete vectors on the right. And now you can kind of see where the lines appear, right? Matrix A doesn't have many lines, but in matrix B, you can now see like there is a line here, and there is a line here, and there is a line here. And this exactly corresponds to the direction, I mean, the orthogonal direction of where this planted vector was put in.
I guess A, because it had too many minus signs.
It had too many minus signs. Actually, I didn't cheat. I did it at random. I did it on the computer. So, you know, that's what randomness looks like in real life. So, okay, so what does this have to do with certificates, right? Well, how am I now going to prove to you that the matrix is like A and not like B? And one way to prove to you like it is I give you a random challenge. I give you a random point somewhere, and I ask you to find me one of these plus minus one combination which is close to it. And if I give you matrix B, then you have no chance, right? If I choose my parameters correctly, because if I pick a random point, then it's likely to fall between two of these lines, and then there will be nothing around it for you to give me. And what is a bit more interesting is that if the matrix A is chosen at random, then you can typically do this. In some sense, if I take a random Gaussian matrix and I take these plus minus one combinations, it's going to fill up space evenly. Each one of the marginal distribution of each of the points is going to be Gaussian, but actually it's going to be statistically close in some sense to the Gaussian distribution. And in what sense is it statistically close? So this is the technical claim, is that if I take a normal matrix A, I hit it by a random plus minus one vector on the left, and then I compare the output of this matrix to a Gaussian vector, conditional on the choice of A, right? So I fixed A, and then I compare the distribution x times A with a Gaussian vector, that this should be close to one another. They're not going to be close to one another. Does anyone see why they cannot be close to one another? Well, one of the distributions is discrete and the other one is continuous. Right? Condition on A, if I hit it with a plus minus one vector on the left, right, then what I get is just, you know, some set of 2 to the m points, right? So it's a discrete distribution. Well, this is a continuous distribution. So these are going to be distinguishable with probability 1. But it turns out that if you do a little bit of rounding, and I'm not going to tell you exactly what this rounding is, but it's quite insensitive to the choice of parameters, then these two distributions do become statistically close. So really, if you look at the previous picture, if I kind of, you know, I round them appropriately, then it does look like what a rounded Gaussian is. And this is we proved this in a paper where we were looking for applications to this to public key cryptography, and describe some crypto system based on this with Miguel Cueto Noval and Charlotte Hoffman and Alon Rosen. So what is the implication for this for the nearest Boolean vector? Well, I would like to use this to certify that the matrix is random, that it's far from the Boolean cube. And it works, but unfortunately, it's not interesting. Okay, or maybe fortunately, no, but it's not interesting. The reason it's not interesting is because to make this result meaningful, and it turns out it's kind of a limitation of this particular construction, is that you need to pick the dimension, the number of rows of the matrix to be, it has to be a very tall matrix. M has to be bigger than n squared. But when m is bigger than n squared, then the nearest Boolean vector problem turns out to be easy. Okay, so why is the nearest Boolean vector problem easy for tall matrices, right? It's because there is this, idea that's, again, it's often used in crypto and also in learning, it's linearization. So what are we looking for? We're looking for some kind of approximate solution to this system of equations. I want to know if there is some combination W of the column vectors here that that will give me something which is close to a plus minus 1 vector. And I mean, this is hard to solve with linear algebra because I don't know what these signs are going to be, whether they're going to be +1 or -1. But if I square both sides, right, if I do some kind of tensoring, then I can get a related equation where the right-hand side becomes just the all one vectors. So if I take the tensor of every row of itself and the tensor of W with itself, then I get some kind of equation which is like a linear equation, right? With 1 on the right-hand side. And if M is much less than n squared, right, then this matrix here is still going to be have more constraints and variables, and I can solve and figure out what W is going to be. So in other words, the nearest Boolean vector to a subspace problem is not particularly interesting when the number of rows is very large, when it's bigger than the square of the number of columns. So this is where like an even older idea from cryptography comes from. So there is actually a crypto system of Ajtai and Dwork, which is better than the one that inspired that I told you about our work just a minute ago, which essentially can be explained as a similar idea, but with one additional twist, which really helps improve the parameters. And the idea of Ajtai and Dwork is this. So again, think about it as I have these two collections of points and I want to know which one is random and which one has some Boolean vector planted in the column space. So what Ajtai and Dwork do is they single out two of these points and think of them as vectors. So the black point here is just the origin, right? This is the old 0 point. And then what they do is instead of doing all these +-1 combinations over the reals, they do everything modulo this lattice, which is generated by these two vectors, just some two points, right? So now the way that you can think about it is these blue points, they fall in different parallel pipettes, but I'm going to work modulo the parallel pipette. So I'm going to kind of put them all in the same one and then see what happens to the distribution. And this is again the picture that we get. So this is what happens when I take some kind of random +-1 combinations, and then, but now I do it modulo the parallel pipette. So the picture here is going to be just what happens inside the parallel pipette, right? So these two axes are going to be the 2 points that we chose. And you see that the left picture looks pretty random. The right picture looks also a bit random, but if you squint really hard, you can kind of still see the lines, right? So there are some lines here. But now they're noisier, so it looks like things are going in the wrong direction for us, right? We don't see the lines as clearly. It turns out that's true, and there is a reason why it's noisier, but it has one big advantage. And so this is this is the way it looks algebraically, their construction. So what they do is instead of working with the matrix A, first they cut out a square matrix P out of it, and they think of this as the parallel pipette modulo, which they're going to work. And then they're again going to compare what happens to the two distributions when I take a random matrix A and I reduce these points modulo the parallel pipette. And what they prove is that it's going to be very close to random. Now it's just a distribution over a cube, so it's going to be uniform distribution. And the advantage is that here it's actually going to be exponentially close. So the statistical parameter is much better than in the other construction. And it also works for the value of M, which is smaller. So it works when M is bigger than n log n. The disadvantage is that the construction itself is more complicated. So this is, you don't have to understand this, but they have to, the algebra that you have to do in order to, put these vectors in the parallel pipette is more complicated, and that costs you in the completeness, right? That these gamma parameters becomes larger because somehow these operations increase the noise. But that's essentially the idea. So one interesting kind of question that came up when we were doing this is that in this construction they have to use this matrix P inverse. So it turns out that when you want to calculate the parameters, to understand what happens to gamma, you need to understand like the distance from the cube, right? The completeness error is governed by, it turns out, what is the largest eigenvalue of P inverse, which is the same thing as the smallest eigenvalue of P. So actually, it shouldn't say eigenvalue; it should say singular value. So it should be. This is not a symmetric matrix, so it should actually talk about singular value. And this is something which has been studied. So if I take a random matrix of normals, then it turns out that the singular value is going to be, with constant probability, no smaller than 1 over square root of n. So this is the factor that you're going to lose. So we need to find inside this matrix A some kind of submatrix P which doesn't have too small a singular value. So how do we do it? Well, if the matrix A happens to be very big, what we can do is we can divide it in independent chunks, right? Everything is random. And we can say, well, at least one of these chunks will have this property. But then we have to pay some price, right? The price we have to pay is that the error, like the fraction of instances for which the algorithm will fail, is going to be somewhat large, right? Because we take this matrix and we partition it into a small number of chunks, right? So the probability would be something like, if we do it in this way, sorry, PowerPoint is acting up, 2 to the minus m over n roughly. And what we show as part of our analysis is that if you do this in a greedy way, so you add the rows of P one by one according to some criterion, then you can actually improve this probability of finding a matrix with a good smallest singular value from 2 to the minus m over n to something like 2 to the minus omega of m. So that's a bit of an aside, but it's part of our analysis. So that's what we do in the paper. So at last, what I want to talk about is, like, after we did this, something that came to our mind, and we're still trying to understand. And one question, natural question that you can ask is, well, the sums of squares algorithms, right? They don't see a solution even in the case of perfect completeness. They cannot even detect that the random subspace does not have a Boolean point exactly inside it. Well, is that the real answer, right? If I give you a random subspace and I just want you to prove to me that there is no Boolean point inside it, then is this a hard problem? And it turns out it's not. It's actually an easy problem, and this goes back to ideas from where people used lattices to solve subset sum problems. And in modern language, they can be actually phrased as a reduction to the shortest vector problem in lattices. So what these reductions tell us is that essentially, well, if I want to distinguish perfect completeness from random, then what you can sort of cook up an instance of the shortest vector problem so that subspaces that have a Boolean vector in them map to instances with a very short vector, while random subspaces map to instances which have a very large vector inside. And these two are actually distinguishable in polynomial time by the famous LLL algorithm. So this gives us a polynomial time algorithm for solving the exact version of NBV, even in the case when m equals n plus 1, even if I have just one more dimension. So now, being a complexity theorist, like, you scratch your head and you think, well, we know that SVP with very large approximation factor has a polynomial time algorithm, but actually we know more. We know that even if the approximation factor is small, we still can do something, right? We have certificates, right? And like for approximation factor m, they're actually fairly simple certificates, but then, like, if you want to push it, then there is this, again, work by Aharonov and Regev, where they showed that even approximation factor square root of m can be certified. So perhaps what is happening here is that, it can be reduced directly to the shortest vector problem, and maybe one can obtain even better and more efficient certificates using a direct reduction than going this roundabout route through cryptography. So as I said, it's inconclusive, but it's still work in progress. So let me finish a little bit early. Well, you can go to lunch, but I just want to leave you with some conclusion and some open problems. So I think sort of the main, perhaps, conclusion of this work is that, this is an interesting problem because again, it's sort of, there is these two parameters, which is the rate and the distance, and they seem to play a big role in the complexity of the problem. You know, when you ship them around, you go from something which is P to something that has certificates to something else that might, you know, not be inside NP minus co-NP, average case in NP minus co-NP. And this is something that is not fully captured by the SOS lower bounds, which is the main methodology that people use to solve these kinds of optimization problems. So there might be, you know, it might be some instance where complexity has something interesting to say about, you know, why this SOS lower bounds or this optimization methods might not give the right answer. So I think the most interesting question based on the motivation here is whether the problem is in QNP for kind of a more realistic setting of parameters where both the rate and the completeness error are constants, some small constants, and that would relate to the motivation of Mohanty, Raghavendra, and Chu. So if you could prove membership in QNP, then you would get at least non-deterministic certificates that beat the eigenvalue bound for the Sherrington-Kirkpatrick problem. Okay, I don't know if anybody outside complexity theory would be interested in it, but at least it's a nice story to tell. And sort of more ambitiously, right, because, you know, as you move these parameters around, you get different behaviors, then you can start asking, well, is there some kind of phase transition? Or, you know, does the other thing happen where maybe if we give the algorithm or the more time, like, so we have like non-deterministic time, sub-exponential time algorithms, then we can get even better parameters, right? And I think something like this does happen for the shortest vector problem, so it might be related to that as well. And finally, I think sort of the big agenda or thing that I'm interested in is if we can find other more natural examples of kind of problems in average case complexity that are, you know, that lie in this interesting space between NP and P, right? So there are not so many, right? And I think all of the ones I know have something very interesting happening in them. They're different features, like this Feige-Kim Ofek algorithm. Like really, you know, they discover a new kind of combinatorial structure that is used to find the witnesses. So I think coming up with more examples might be, you know, a good place to go to understand a bit more what is happening in average case complexity. So I will end here. Thank you.
Questions for Andrej?
Do you have a guess as to whether in VV with these constant parameters, like whether you think it should be in GONB or?
I think it shouldn't. I mean, it looks like it shouldn't. If you look at the analogy with the shortest vector problem, I think below, like when n over m is sub-polynomial, it shouldn't be. But again, I mean, it would be good to have some evidence. Like for shortest vector problem, at least there is some NP hardness in the worst case that people used to argue that you cannot solve those kinds of problems. Here, I think even the worst case problem, as far as I know, is not very well understood. So I suspect that the answer is no, but I don't know why.
Like, what would you base the hardness on? Like,
well, the first thing I would like to know is the worst case version of this problem, right? For these parameters, is it NP hard? I don't know.
This isn't a particularly like clear question, but you know, it looks like you're trying to relate this problem to the last problems. I'm wondering if you've thought at all about connections to like planted clique.
If it's possible to connect this to planted clique. Well, I mean, again, like for the setting of parameters that we looked at where it's inside CoNP, as far as I know, planted clique is outside, right? It's outside CoNP. So we wouldn't expect a reduction from planted clique to this. This, if you can reduce to planted clique, I have no idea, right? So, I mean, it's a good question, especially like in this picture that I gave you, right? A lot of, okay. So planted clique is actually important in some of these applications. Like if you can read backwards, it has the planted clique row conjecture written down, right? So that's the basis of all these reductions. So in fact, if you can reduce anything to clique, it would be very interesting, I think. I mean, they need some special version. It's not like the usual planted clique. They needed some multipartite graph and so on and so forth. But again, I don't know. I don't see a planted clique structure, like average case kind of planted clique structure in here. But who knows?
Any more questions? Let's thank Andrej one more time.
Thanks.